Chapter 6. If you thought the last section was fun, this section is even more fun. Each section in this class gets funner and funner. Yes? Okay. So, the point of this chapter is comparative statics. And getting us started onto this idea of what a derivative is. A little calculus. Okay? Remember that comparative statics means in economics mostly we're going to look at one equilibrium position versus another. So we're not looking at how we got from point A to B. We're looking at how point A is different than point B. All right? How are we different versus how did we get there? Okay? So we're not looking at the path we took. So we started in Vegas, now we're in LA. We're not worried about did we fly, did we drive, did we take the train, did we ride the bus. We're worried about the difference between where we were in Vegas and where we are in LA. Okay? 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 Okay. Now, what matters under these things then is the change. How much change there is. And how we figure that out is the difference, the rate of change, right? What's important is the rate of change in comparative statics. The rate of change and the direction of change. So he said, let's talk coronavirus for a second. Okay? If you turn on TV, you see these, 130,000 people have died, and there's this many cases. And to someone who is a math econ kind of person, your first thought would be, those numbers don't matter. And I'm not saying that 130,000 people being dead don't matter, right? It's horrible, right? When you think that there's fewer than 1,000 people dead in Korea and fewer than 1,000 people dead in Japan and 130,000 people dead in the United States. And in fact, if you actually go to the government websites and look at the data, because we're data people, and you even ignore the idea that maybe what's written down on death certificates is wrong and there's fudging, that 130,000 number is probably low. It's probably closer to 200,000. If you actually look at the data on how many people have died in the last few months and all that, right? I'm a statistician. I don't listen to newspaper guys or guys on TV try to tell me what's going on. I go look at the actual data, okay? But what matters here are data that we don't see, for example. So what it should be showing us on TV is how many people have died per day and what's happening to the rate of people dying per day, the change. So what we know is that from March to April to May into the early part of June, the number of people dying every day was going up, and then the number of people dying every day started going down, and it was, at the peak, it was like a couple thousand people dying a day, and then it went down to about 300 people dying a day, and now it's back up over 1,000. So it turned around, and it went back up. So to us, we're looking at the rate, we're looking at how fast it's going up or how fast it's going down, and then we're looking at, is that rate changing? Is it going up, but going up more quickly over time? Is it going up, but going down more over time? Okay? Yes? And then the other thing we look at is the test positivity rate. So we're doing more tests, and more of them are coming out positive. But what about the percentage of tests that's positive? That's a key indicator, not how many tests we have or how many are turning out positive. What percentage of the tests are turning out positive? So a month ago in Florida, 4% of the tests were turning out positive, and now 30% of the tests are turning out positive. So we're seeing the change, right? The number of cases going up. But that positivity rate is telling us that it's going up at a faster rate. Okay, so it's not that just that it's going up, but the rate at which it's going up is increasing. The rate of change is increasing. Okay, what you want to see is that positivity rate going down at an increasing rate. And what you want to see is the number of people dying per day going down at an increasing rate. That means we're getting in control and we're getting rid of this thing. When everything's going up at an increasing rate, that's just the opposite. That says to us, hey, something's out of control here. Okay? But it's the rate, direction and rate of change that's sending us the message about what's going on. Okay? And, well, none of the people on TV seem to understand that, which means they need to come take some, math econ or something. Okay? Okay. So. What we talk about in this world is something called, or to start in this world, is something called a difference quotient. And a difference quotient is really simple. It's the change in y divided by the change in x. And we all know that that's a lowercase delta. Okay? So you have a function, y is a function of x. The difference quotient is the change in y divided by the change in x. Okay? You with me on that? The change in y divided by the change in x. And we can write it out a different way. We can say, since y is a function of x, we can write this out in terms of x. Okay? And we're going to use something called x0. x0 is the starting point. It's where we start. All right? Plus the change in x minus the function for f0, okay, divided by delta x. Now the whole thing's in terms of x, right? So this is our starting point plus whatever the change is, and this is just our starting point. Run through the function. So if our function is y equals, 3 plus 2x, if x0 is 10, then this is right? That's 10. 10 goes in there. I get 23, right? So this would be 23. If delta x is 2, yes? So x0 is 10. X now would be 12. This goes up by 2. Put 12 in here. Yes? Is 27. So this is 23 plus 4 minus 23. Yes? Divided by delta x, which is 2. Yes? Yay. Okay. You're saying, what's the point of this? Well, 27 minus 23 over 2 is 2. All right. Delta y went up by, delta y is 4. Delta x is 2. What's that 2 say? Well, x changed by 2 y went up by 4. For every 1 change in x, I got a 2 change in y. So for every 1 change in x, I got a 2 change in y. So if x changes by 2, y changes by 4. Is that exciting? That is really, really exciting. No? Yeah. What did that just sound like? Yeah, it just sounded like the slope of the line, right? Delta y, delta... Yeah, that's what it is. Okay? We're talking about the slope of the line. This is just a really fancy way of finding the slope of the line. And that's really the slope of the line. Okay? Now. The problem with this isn't when we have that. The problem with this is when we have that. Okay? And you're like, really? I don't want to go there. Yes, you do. So, let's look at this line. Okay? The slope of this line, this slope, changes with every point. We can find the slope. If I want to find the slope at that point, okay? I want to find the slope at that point, call it A. Slope at A is the slope of the tangent line. So if I draw a line, a straight line that just touches that curve at that one point, the slope of this line is the slope of the curve at A. And if I pick point and call up here and call it B, the slope of the curve at B is the slope of that tangent line right there. So delta y over delta x. So as this curve, as we go up this curve, the slope is getting steeper. Okay? Delta y over delta x is getting bigger. The slope is getting steeper at every point. Well, if we try to do this, if we try to do the straight line thing and calculate delta y over delta x and just, it's not going to work, okay? The closest thing we can do is draw that secant line. So that's a straight line. You want me to do that again? Okay, I can take point A here and point B here, and I can draw a straight line to connect them. Okay, and that line is the secant. The slope of this line, delta y over delta x, right? The slope of this line is the average of the slope of the curve from there to there. So the green part of the curve, the average slope along there, is the slope of that secant line. Okay? And I know how excited you are by that idea. Now, if I take B and I create a new B and put it there and draw the secant, and put a new B and put it there and draw that secant, and put a new B, the shorter I make that secant line, the less that average is going to differ from the actual point. Okay? What I really want to do on this line is find a secant line that's so short it basically isn't there. Okay, I want two like 2 points that are next to each other almost. And that means, since there's an infinite number of points and they're infinitely close together, we're not doing that with regular math. Okay? So the best we can do with normal math is to find a secant line, which gives us the average across this curve. You do not want engineers building things off of that secant line. You want to know what the exact slope is at A when they do this. You don't want to go, well, the average around there. No. Please. No. Okay? Everybody with me here? I need to find the slope of that line at that point. Okay? I need to find the slope of the line at that point. And we're going to do that with something called a derivative. Now there's a whole big argument about who invented all this stuff. Usually normal people give Isaac Newton, credit for inventing this stuff. Lots of old mathematicians knew pieces of it beforehand. But in truth, the methods and all this stuff that we do came from this guy named Gottfried Leibniz, not from Isaac Newton. But Newton kind of wrote it down and published it first, so Newton gets the credit, even though his thing wasn't as complete, his world wasn't as complete. And, Leibniz did it first, and the two of them, argued about it forever. And then other people have argued about the Newton versus Leibniz thing for hundreds of years, but just ignore that part. Okay. So we're going to talk about now a derivative. The definition of a derivative is derived, and we're not going to do the actual derivation, from something called a limit. Okay? A limit. So we had this thing, right, where we're looking at, x0 plus delta x, right? The only thing that's really in question in this is delta x, right? Delta x, that's a delta. It's a little tiny delta. Okay? What we do in the limit is we say, what's the value of this? So what's the value of this equation, right? So this is delta y over delta x. What's the value of this as delta x approaches? And we use this arrow, and that arrow is approaches some number. And the number that we're going to pick is 0. Remember, on this line, 2 points that are right next to each other are going to have a different slope. What I want is that secant between them. So the secant between them is still the average of between those two. It's not the actual point. But if somehow I could do the math where that secant actually had a length of 0, then I'd be finding the value at that specific point. And I know you're like, really? It's summer school. Yes, this is so much fun. Thinking is good for you. Okay? So we're going to change our notation. And we're going to use the letter D. And we're going to say dy dx, which is the derivative of y with respect to x. Okay? And all the derivative is, again, is the rate of change. It's the slope, but it's the limit, a derivative, dy dx, where y is a function of x. We also write this by putting the little prime symbol up there. Okay? That means we're taking the derivative of this function. Okay? It's the limit as delta x goes to 0, okay, of this dy dx, delta y delta x. So this difference quotient, right, that's the difference quotient, delta y delta x, what's the value of this thing as delta x gets smaller and smaller and smaller and smaller and smaller? Yeah, you're so excited by that. Okay? Yay. No? Well, we did y equals 3 plus 2x, right? Yes? Yes? We'll already know what the answer to this is in this equation. Okay? What's the slope of this equation? Right? dy dx is the slope at 1 point. And again, that is easy, right? That's 2 over 1, that's 2. The slope of this line is 2. I already know if y equals 3 plus 2x, I know that dy dx somehow has got to equal 2 because dy dx is the slope. Okay? Yes? Okay, fine. If it's y equals 3 plus 2x squared, now I have a problem because now 2 isn't the slope because this thing is going to look like that. And the slope is not a constant. It's changing. The slope is a function. All right? There's an equation for the slope now, where in this case the slope is a constant. When we calculate the slope of this, what we need is an equation. And you're like, listen to me, it's 115 degrees outside. There's no point in doing anything but sitting inside and working on your calculus. Okay? There is nothing better to do. Yes, it would be better if we were sitting in a classroom and we could all share the pain. But, this will make great little TikTok videos of you doing your calculus, yes? So just trust me on this. No? I should put some on paper. I have Instagram photos from last summer when people were posting Instagrams of them over in the library with whiteboards solving calculus problems. Because what is more fun than doing that? Okay? And assuming the library opens at some point here and you can go do that, you should maybe even think about going and do that. Wear your mask, but you should think about maybe going and do that. Okay. Okay. All right.